Yeah, hello. Today I'm going to talk to you guys about the time enclosure, how to speed it up, and also talk about the physical planning. My name is Himanshu Bhatnagar. I'm the CEO of Excellicon. And so let's start. Okay, so the agenda today is we're going to talk about the basic, ASIC flow and what are the challenges. Then I'm going to introduce some products which can help you in this area. We're going to talk about the constraints, promotion, demotion, budgeting, SDC generation, and then timing equivalency checking. This is a new topic, so I'll spend some more time on it to introduce this topic. And then we're going to go over the constraints verification, management, and finally the clock tree analysis, verification, and physical planning, floor plan verification. Floor plan verification is also a newer topic, and it's more like a shift left methodology. So we're going to talk about how to do the floor plan verification at early stage and not at the later stage. So with that, let me first go over the current ASIC flow. So the current ASIC flow is if you have two bars, the front end and the back end. So the top bar is you start with the design and integration. This is where the chip is, you're buying IPs or you're developing IPs, you're integrating the whole chip and all that sort of thing, and then stitching the whole fabric together of a SOC. Then majority of the time you're going to spend on the functional verification, and this is where you're running test benches, regression, and all that sort of thing. So that happens a lot. Then at the same time, the backend staggers a bit because while the design integration is happening, there may be a few initial implementation efforts there, but majority of things starts when at least the design is all stitched up and all that. And then you're gonna go over the basically two bars: initial timing closure and the final timing closure. Now, the initial timing closure is your there's no such thing as initial timing closure or final timing closure, but you know the reason I carved it out is because initially, there's a lot of activities you're gonna do synthesis, you're gonna do constraints development, you're gonna do flow planning and all that thing until the implementation kind of stabilizes and you are in the static timing analysis phase. Once you're in the static timing analysis phase, then the final timing closure is where you're fixing the setup and hold. You may be doing some ECOs and all that sort of thing. Now, the initial timing closure phase takes a long time because there are a lot of unknowns there. And you at the same time, the back end guys, they're always interacting with the front end guys because the RTL may change. It's constraints are being developed, and that's a big topic here. Flow planning is going on in parallel. There are a lot of reviews happening, and all that information is getting in from the front end to the back end, and driving the all these decisions for the initial timing closure. Then after that, you're going to do setup and hold fixing. Now let's go into the challenges in the ASIC flow. Now, constraints development, that's a big topic. That's always, it's a very iterative and the tedious process, and really no one knows whether your constraints are correct or not until you validate them with a tool or something. And then constraints also, because the constraints, there are different types. So for each block and different modes, you have so many different constraints. So let's say if you have a chip with 5 blocks, and there are 3 different modes: functional test and functional scan, capture, scan, best, or something. That's 3 modes right there. Generally, people have more. And so that's like a 3 constraints for each block. And if there are 5 blocks, then that means 5 times 3. And then you have variations that you may have want to do full flat STA, or you may do some hierarchical variation of the STA. So the volume of the constraints, they multiply. Also, sometimes you have constraints to the lower level. You want to promote it to the top level to build it up. And that's a very tedious task. when you have a design optimization tools like synthesis or place and route, they optimize it. Maybe they're doing some cloning, decloning, or boundary optimization. These kind of things, they always impact your constraints, and some of the paths may change, and that could really invalidate your timing constraints. Lastly, the gate level sims is still being done, but why are we doing it? Mainly for double checking the timing constraints. Previously we used to do it to find out the glitches and clock domain crossings and all that. But now you have tools to check all these things, static tools. So still we do the gate level sims just mainly to check the timing constraints, because rubber meets the road only at the gate level sims. Okay, now let's go into the clock tree implementation. In the clock tree implementation, clocks are the heart of your chip, and with complex chips, it's very hard to understand the chip clocking. And generally, as a SOC designer, you draw it out on a piece of paper or use Microsoft Visio or something to draw the clocking diagram. And then you understand how the clocks are propagating, how they're muxed together, whether they're blocked due to static value or what. So that's a major part of the clock tree design itself. You have to first understand it before do the implementation of the clock tree. Clock tree, as I mentioned, is the heart of your chip. Yet, there is no such thing as validating the clock tree, whether it was implemented correctly or not. For example, if you have excessive buffering or you have redundant logic in your clock tree path, you'll never know. And that is until there is some sort of a timing violation, then you start realizing and analyzing the clock tree. So there's not any tool which can actually validate, verify whether your clock tree is implemented correctly or not. Lastly, the skew groups. Skew groups, as we know, they help in the timing closure effort, right? Now, what are the real screw roots? Today, you have to basically analyze the RTL or netlist, and you need to understand how do I carve it out so that I can actually get some benefit out of the skew groups. So all these things actually impact your clock tree implementation. Floor planning is another activity where there's a significant challenges. When the RTL comes in, let's say you have a large SOC, and when the RTL comes in, there's a what is the area? How much power is going to consume? Is the performance going to be okay or not? How is the clocks are going to getting distributed? How should I carve out my partitions so that I can have a better time in the timing closure? What should be my correct partitions? So all these things are there driving the floor planning. Again, for physical synthesis, if I have an RTL and I get the physical synthesis, I don't have physical data. It's just a pure RTL. So how do I get the physical data? Today, I have to do a logic synthesis, then I have to do floor planning, then I have to do physical synthesis, and go back into the logic synthesis for floor planning data, and then I have to then use that for physical synthesis before I go into the place and lab. How do the partitions interact? The floor planning, is it truly reflected to the RTL? There may be some areas where the RTL has some, let's say, glue logic between the partitions, yet in the floor planning, you're abutting the partitions. So all these kind of issues lead to the floor planning. And this is a very iterative process, a lot of back and forth going on. And the problem is that the backend guys generally don't know the functionality of the chip. And this is where the information needs to flow from the front end to the back end. Okay, so on the constraint side, this slide, I just want to quickly go over the slide that the constraints is today the major component driving all the downstream tools here. So you have FPGA, synthesis, static timing as a placement out, power, CDC, and everything. All these static tools requires SDCs as a seed input. So getting early SDC as soon as possible is very, very important. Other thing is there are flavors of the SDCs. You have also different flavors. For STA, you may need one flavor. For let's say CDC analysis, another flavor. For test, another flavor. CTS is we use kind of a merge mode SDC to drive the CTS implementation. So the different flavors, so the volume of SDCs, they actually grow. And that's why it's very painful to develop SDCs and maintain SDCs. So let me introduce the products which we have, which help in all these areas. So we have 4 products: the Kanban, Concert, Contri, and Construct. The Kanban and Concert, these are the ones which are in the constraint space. And there's some description on the next slide for each of the products. The Contri and the Construct. Contri is for your clock tree analysis, implementation, skew groups generation, and all that. And Construct is your RTL flow planner, a partition analysis, and the verification of the flow plan itself. Okay. So there's a lot of details in this slide here. I'm not going to go over each of them, but you can review it at your own time here. For all the 4 products, what are the features for each of these products here? Now let's go quickly into the promotion, demotion, and budgeting. This is one of the critical components of chip development. As we know, sometimes we get SDCs, tickle SDCs, I should say, for IPs, and now for the top level, we don't have anything. So the tool can automatically promote any SDC. If you don't have SDC for some of the blocks, it will generate it. But if you have it, promote it to the top level as fast as possible, because the moment you get to the top level here, the world opens up for you. You can actually then drive other tools like CDC analysis or static power analysis, and the moment you get that constraints for the top level here. So this is also represented in this diagram here, that you can promote it to the top level, and then you can demote it to the partition level, the ones which you're carving out for hardening. So you can demotion, budgeting, and promotion, and so these go pretty much hand in hand. And they can also use the tools to write out hierarchical SDC budgeted with .libs. So the tool also have the capability to write out the .libs. This way you can have manage all the variations of SDC here. The budgeting methods and types. The budgeting can be done with 3 different types. You can do fine grain, coarse grain, or manual. And budgeting calculation is percentage based, logic levels based, and delay based. Obviously, the percentage based and logic levels based, you can do it at the RTL level. At the gate level, you can do pretty much all 3 here. And this way, once you do the budgeting and then you drive write out the SDC, you have significant good chance of doing a timing closure, and your power is going to be also managed nicely, because you're not over optimizing the boundary interfaces here. This is another example of how do you write out a hierarchical SDC with the .lib models here. And you can do the first demotion budgeting, then you simply just write out the SDC here. Now let's talk about the equivalency checking. This is another area which is gaining a lot of traction here, because the tools which do synthesis and place and out, they're really optimizing your design quite a bit. New paths are being introduced, new paths are getting eliminated, registers are getting eliminated. So with all these things, your original timing constraints may not be valid. So as we all know, the chip comprises of 2 components, functionality and the timing. For functionality, you verify through logic equivalency checking. And we all know about the logic equivalency checking. No one tapes out a chip without doing logical equivalency checking. But the other component is timing. And there's no such thing as TEC today, which is timing equivalency checking. And this really is, you need to validate your chip for TEC before taping out. For example, and this actually happened with the customer of ours. So there was a CPU running at 800 megahertz and the NOC running at 400 megahertz. And the registers NOC multi-cycle path of 2 against the CPU registers here. So the guys, they put a multi-cycle path of 2 through this port P1 here. Now, what synthesis was done at the whole top level here, and the synthesis tool actually did a good job in optimizing the boundary interfaces. So it basically coupled these 2 logic bubble, put it here, and routed the signal here. which is the right thing to do. They ran LEC, and the LEC came out clean. This is 100% equivalent. Now look what happened. The original constraints were applied on this also, and the multi-cycle path, previously it was only the knock block registers were multi-cycle path of 2. Now this entire thing, the some of the CPU registers also got multi-cycle path, because dash through was impacting this knock block as well as the CPU block here. And this was caught only 2 weeks before tape out, and the whole thing got delayed because of that. So these are the kind of issues which happen because of the optimization happens, cloning, decloning, all that sort of thing happen. You cannot assume that the SDC, original SDC, is still valid. You need to ensure that it's equivalent to your to the new one. So this is where we introduce the equivalency checking flavors. So traditionally, the equivalency checking has been top to block, which is top level, against the block level here for consistency checking. Then there's the top to top flavors here: 1D, 2S, 2D, 2S, 2D, 1S, etc. For example, 1D, 2S design remains the same, but your SDC changes, okay, as the design progresses. 2D, 2S, 2D, 1S is more interesting. Here, the designs are different and the SDCs are different too. So you have design one and SDC, for example, RTL and SDC, gates and SDC. Or this one is pre-ECO netlist, post-ECO netlist, and the SDC remains the same. So you need to make sure that all the timing equivalency is done properly before taping it out. There are many other flavors also, merge mode to multiple mode and all that sort of thing, but the top ones are the more interesting ones here. Okay, now let's go into the constraints verification features. So constraints is you need to validate the constraints, not wait for the gate level sense, but you need to validate the constraints as soon as possible. So our product concert will make sure that statically it will validate all the constraints, and it will also actually generate you a clocking diagram if you're into at a more abstract level, so it's easier to understand. It has full waivers capabilities. You can write out the waivers. You can promote the waivers also from block level to the top level, so it doesn't fire again. You can change the severity. You can create your own custom rules. It has a full GUI as well as schematic viewing capability and fully cross-probing and all that. The constraint simulation, this is a kind of a new topic, and some of the constraints cannot be validated by the constraint verification. For example, here we have a formal method for validating false path, multi-cycle path, and all that also, right? Now, but let's say you have a programmable divider, clock divider. Now, software is controlling that programmable divider. So how is the waveform coming out of a divider correct or not? So those kind of things, no tool in the world can validate it. Another thing is false and multi-cycle. These are your timing intent false and multi-cycle path. Let's say you have a configuration register and you put a multi-cycle path of 2 from a configuration register for timing relaxation purposes. It's not a real structural multi-cycle path or a false path. Is that correct? So we also have the thing from you can write out basically system verilog assertions for those things which cannot be validated by static constraints checking tools. And system verilog assertions, you can apply it with the test bench and that will catch it. Okay, the beauty of that approach is that why do we do gate level sims today? Previously, we used to do it for glitch analysis, for CDC analysis, catching things which cannot be, because there were no tools, static tools to catch those things. However, now we do. We have formal verification, LEC. We have glitch analysis tools. We have CDC analysis tools. So why do we still do gate level sims here? The purpose is we are revalidating timing constraints. And so the good thing about this approach is for you validate your constraints statically through our tools, and then write out the SVAs for those things which cannot be validated, and then you put them as part of your test bench. So this way it eliminates the dependence on your place and route in SDA and SDF pretty much. for your simulation. So you're not waiting for the time enclosure to finish and before simulating. Okay, you can do it as early as possible. Finally, for the management on the constraint side, we have also interfaces natively. You can manage all the different mode, the different constraints for each blocks and all this sort of thing. Or you can write out a text file called ECS file, which goes straight into the Excel spreadsheet. And here you can do the management of your constraints. You can add clocks, delete clocks, change the values, do whatever you want, and then write back into the ECS and into the SDC here. So this is all part of that. Now let's talk about the clock tree analysis and verification. So this clock tree tool, as I mentioned before, it is clock tree is the heart of the system. And you know, so what the clock tree, the clock tree tool does, it will analyze your clock tree. So obviously, this relies on the clock tree has been implemented into your tool. It's not implementing the clock tree, it's analyzing your CTS. Okay, so so you can analyze your clock tree at the pre-implementation level and then the post-implementation level. Okay, so you can look at let's say RT, you run country on the RTL, you analyze it, understand how the clocks are propagating. You can debug all these clock trees. You can even generate the skew groups, and then how the clocks are merging together. What are the case analysis driving these clocks? Are they blocking or not? What is the relationship? How are they synchronous or not synchronous or asynchronous to each other? So all these kind of things are you can do full analysis. And then the verification is another component. If you have implemented the clock tree and the clock tree has got what are my exclude pins? What are my, is any excessive buffering going on? Maybe you have back-to-back buffering, back-to-back buffers going on instead of back-to-back inverters. So, or is the derating going to be affected? So all these kind of things are done as early as possible, so you can have a better implementation of the clock tree, and you're not gonna, burn excessive power in the clock tree, or timing closure issues not going to happen. So this is part of the clock tree analysis. So this is our product country. Now, lastly, our last product construct is this for partition analysis and for floor planning. Okay. Now, when I say floor planning, it is talking about the verification of the floor plan and all that. Okay, sorry, this slide here. So the construct is doing partition analysis. When the RTL first comes in, what constitute a correct partition? How do I carve out the chip? So I have to look at the area, I have to look at the timing. Let's say I want to partition the chips such that all my partitions are asynchronous to each other, and the synchronous behavior is within the partition. How are they connected? How is the data going to flow from one partition to other? So all these things, you can, the tool can do the what if scenarios without modifying the RTL. So you can say, I want to lump this and this IPs together and tell me if I were to combine these two, what is the area and how's my timing going to look like? What are my critical paths and all that sort of thing. So this very quickly does a full partition analysis without modifying the RTL. Now, what if you want to modify the RTL based on the tool? Or you can do it manually. Most people like to do it manually. Or you can automatically do it, ask a tool to do it, RTL partition. So this is another, it will generate a new RTL for you. Third thing is the RTL floor planning. You can, so this is going at the RTL level. You don't need to go into physical you don't need to, basically when you first now have an RTL, today the flow is you have to synthesize, then you have to go into the floor planning, and then you come back and do the physical synthesis. You can eliminate all this thing by doing RTL floor planning, and you can create shape move blocks, or you can automatically tell the tool, okay, you tell me what the right floor plan is. Lastly, the floor plan verification. This is very important. Verification is as early as possible. You want to validate your RTL against a floor plan. abutment issues, feed-through issues, routing issues, timing issues, all these kind of things. This is a complete new concept, but doing it at the RTA level. So this is the end of my presentation. Thank you very much. If you have any questions, please ask right now. Thank you.